So, okay, here is all of this together in one problem. Um, each of these is 2 meters long. The mass of each one is 20 kilograms. The angle for each one is 70 degrees. And there's an applied external load of 200 newtons that way. And we want to calculate the internal loads in each one of these. So first, you have to go through calculating the external loads, solve that structure. I'll call that body 1 and that body 2. I'll call this A, B, C. So free body diagram of 1. We have RA up here. At the center, we have a weight of 196.2. Down here, we have the force on 1 by 2. And since the pin is part of member 1, we also have that 200 Newton force. I'll put my about point down here. So F12 has a row vector of 0. The force is F12x, F12y, then 0. The 200 Newton force, row vector is 0. Force is 200, 0. Cross product is 0. Then I'll go up to RA. The row vector there is 2 times cosine and sine of 110 degrees. So that's negative 0.684. Positive 1.79, no, 1.879. Forces RAX, RAY. And so the cross product is negative 0.684 RAY minus 1.879 RAX. And then last is the weight force. The row vector is negative 0.342, positive 0.940. The force is 0, negative 196.2. And so the cross product is positive 67.10. So the first 3 equations, first one is F12x plus RAX is equal to negative 200. Second is F12Y plus RAY is equal to positive 196.2. And the third one says negative 1.879 RAX minus 0.684 RAY is equal to negative 67.10. Okay. And then we'll go to the second body. At the bottom, we have negative F12. At the middle, we have the weight force of 196.2. And then at the top, we have RC. I'll put the about point at the bottom. So for negative F12, row vector is 0. Force is negative F12x, negative F12y. Cross product is 0. At the top, we have RC. That row vector is 0.684, 1.879. The force is RCX, RCY. So 0.684 RCY minus 1.879 RCX. And then the weight force, that is at 0.342, 0.940. The force is 0, negative 196.2. And so the moment is negative 67.10. And so our equation 4 is negative F12x plus RCX equals 0. Then negative F12y plus RCY is equal to 196.2. And then the sixth equation says negative 1.879 RCX plus 0.684 RCY is equal to positive 67.10. So here are equations 1, 2, 3, 4, 5, 6. And variables, I'll say RAX, RAY, F12X, F12Y, RCX, RCY, and the constants. Okay, so the first equation, RAX plus, okay, so RAX 1, F12X 1, constant negative 200. If you find a mistake I make, I'll be happy because I did this right before class and my answers I don't think are right. Then F12Y plus RAY is positive 196.2. So RAY is 1, F12Y 1, constant 196.2. And then RAX, we have negative 1.879. RAY, negative 0.684. And the constant is negative 67.10. And then the next three equations. F12X, we have negative 1. RCX, we have 1. Equation 5, F12Y, we have negative 1. RCY, we have 1. Constant is 196.2. And then for 6, RCX, we have negative 1.879. RCY, we have positive 0.684. Constant, we have positive 67.10. When I looked at it, I was thinking these answers needed sort of a symmetry of compression and tension. And this is why I was thinking that. If you made this thing just a truss without weights, you would have pure tension in member 1, pure compression in member 2. And they would be the same value, just opposite signs. But with the weights in here, I guess now that I think about it, it makes sense that there's not that symmetry because the weights are contributing to tension in member 2 and a tension in member 1, which, adds to the tension in the one that's in tension and offsets the tension in the one that's in compression. So I guess there's no reason to expect that symmetry. So, okay, I'm happy with that. I did double check my answer, and so I was confused why I didn't find a mistake, but I think that's why I think this is right. So RA is equal to negative 135.70, 470.91. F12 is negative 64.29, negative 274.70. And RC is negative 64.29, negative 78.51. Okay, so we're going to go into the internal loads now. Before I do that, I was just talking about if this thing was a truss, if we didn't have these weights. Well, these answers would be terrible if we didn't include these weights because the weights are as big as the other external force first, But if you had a problem like that, let's say that we got let's say that what we came up with was a tension in the first body of, let's say 500 newtons. I don't know what it would be. And then a compression in body 2 of 500 newtons. Okay, let's say we got those for those F1 and F2 forces that we would get for a truss. Can anyone tell me, do it in your heads, what the internal loads would be in those members? if this was a truss. So this is always true of trusses. So that first body that has that F1 of positive 500, okay, it would have an internal tension of positive 500, an internal shear force, an internal bending moment of 0, because that's what trusses do. They're just in pure tension or pure compression, every body, okay? And that second body would have an internal tension of negative 500, meaning that it's in compression, and shear force and bending moment of 0 everywhere, okay?
So yeah, does that mean that trusses would never have anything as a function?
That's right. Trusses, because any two-force body that's straight can only have internal tension. If it's curved, the rules of trusses still apply, but then you do get some, well, we're not doing anything with bent internal loads with bent bodies, but then you would get some other internal loads because, you know, if this thing was curved, those coaxial forces would be tending to like wishbone this thing, you know, if you can picture that. But for straight members, yeah, trusses, all you have is tension. And the tension or compression always just equals the external load value that you calculate. Okay, but that's not true with these. So let me give you a minute or two to just draw the external loads on each of these bodies so that then we can go to the rotation matrices. So that was the one, body one is like this. And we had RA up here, so that one's easy. That's just negative 135.70, 470.91. The bottom one, now this is not just going to be F12. You have to also add on that force vector of 200, 0. So this is, well, it comes out to be positive 135.71, I guess, with the round off error I have. But these have to be in equilibrium, so those have to match. That's the only horizontal force.
I think you actually just rounded wrong.
Oh, okay. So this should be...
It should be 7-1. They should both be 7-1.
Oh, both. Okay, and then negative 274.70. And the y values don't cancel each other because we still have the weight to put in. And the weight is a uniform distributed load. And that is a total of 196.2 divided by 2 meters. So this is a distributed load of 98.1 newtons per meter. And then for the one on the right, at the bottom, now on this one we only have negative F12, so this is 64.29, 274.70. I'm going to move that over. Up at the top, we have negative 64.29, negative 78.51, and then the uniform distributed load for the weight. And again, that's 98.1 newtons per meter. Okay, so for each of these, how many cuts are we going to have to take?
One.
Just one, yep. between the two endpoints, there's no point loads, there's no changes in distributed load function. So now we'll go to the internal loads on body one. Yeah.
So on these, like when you do the way we've been doing it, you keep all those numbers the same in your cuts, and the only thing that you're changing is instead of representing that weight force, you change that to the distributed load.
Yeah, right. Right.
Okay.
Yeah. I mean, I'm just doing it here to remind you that if you treat that weight force, if you continue to treat that weight force as a point force at the center, you're kind of getting an approximation, kind of like a numerical approximation type thing of the right answer. It does have some meaning, but it's not really the right way to do it, you know? So this is where you have to switch to a distributed load. Okay, so now we're going to use the rotation matrix. And I don't know, which way do you want to, you know, the closer they get to vertical, the more kind of visual sense it makes to use either one of the two coordinate systems you could use. But we're going to start, you know, our values now are in this coordinate system like you're used to. Loser. And then we're going to, let's rotate it to this coordinate system here. Okay. Okay, so what rotation do we, so if we're going from this to this, what's that theta that we're going to use?
-70.
Exactly, yep. And so our rotation matrix is going to be cosine of -70, sine of -70, negative sine of -70, cosine of -70.
Isn't that backwards though? Aren't we starting at the tilted y and then going to a straight one?
Yeah, that's why it's so. Remember to think of it in terms of what the coordinate systems are that we're using and not the bodies that we're using. So, because what it feels like we're doing is going from a body that's at an angle to a body that's horizontal. But really what we're doing is going from a coordinate system that has this relationship to this tilted body to one that's aligned with the tilted body, okay? So if you think of taking the tilted body and rotating it straight, you'll always get the backwards, you know, the opposite angle of what you want, okay? So that's gonna be always a thing with coordinate system transformations. You always have to be clear. I mean, you always have to be clear about whether you're rotating the body or rotating the coordinate system. And actually, you can use a similar but kind of opposite rotation matrix to rotate bodies. I just always rotate coordinate systems. Whatever one you're doing, you can always do it either way. But if you try to do it both ways at different times, you're going to screw things up. So I just always rotate the coordinate system. Okay, so now take a couple minutes and see if you can change all of these loads. So what loads do we have? We just have 2 point loads we have to transform, and then 1 distributed load we have to transform. We have this point stuff over here on the left, negative 488.9193, 33.54. And then the way these distributed loads come in, at the center, we have 92.18 times x, because this is a uniform distributed load. You can think of it as like a rectangular shape. And then we have a downward one of 33.55x. And then our internal loads, tension, shear force, bending moment. And so Newton's second law says negative 488.93 plus 92.18x. Why am I not doing this as vectors? 33.54. This is negative 33.55x plus t negative v is equal to zeros. And so t is equal to negative 92.18x plus 488.93. And v is equal to negative 33.55x plus 33.54. And then the bending moment, the moment equation. My about point is at the left, like always. The horizontal distributed load doesn't produce a moment. And so we have a clockwise rotation from that 33.55x with a moment arm of x over 2. Plus m minus vx is equal to 0. So m is equal to 16.775 x squared minus 33.55 x squared plus 33.54 x. And so m is equal to negative 16.775 x squared plus 33.54 x. And if you plug x equals 2 into that function for the bending moment, you get negative 0.02 is what I got with the round off error. What we got a bending moment of, you can see that at x equals 0, the bending moment is 0. At x equals 2, if you don't, worry about the round off error, we got 0 at that end, 0.2. That's because there's no point couples at either of those two ends. And so all of these rules still have to apply in this case with the funky coordinate system and everything. So let's see, dm dx is equal to v, dv dx is equal to negative q, and so everything works. Any questions about that? Okay, on Wednesday we'll finish this, and I guess I'll give you guys more time to go through everything on your own on Wednesday. Let's do the quiz.